Okay, hello, welcome back. So now that we have looked at translation of a rigid body, next step is to look at the rotation about a fixed axis. It is also a planar motion, and just to remind you, what is the definition of rotation about fixed axis is that every point moves around parallel circles, and all of these circles have their centers on the same line, and that line is the fixed axis of rotation. It must be fixed. So we want to study this motion. Before we really get to study motion of each of the points, like point P on this moving body, we need to develop the tools that we need to study rotation. Believe it or not, we actually haven't discussed and don't have the tools about rotational motion yet. And this is the first place that we are going to properly define them. So let's do that. The first thing we need to define is position, or let's call it angular position. Yeah, let's call it that. Angular position, or simply angle. To define angle, we need to consider a line on a body. Any line can work, but for now I'm going to take this line from the center of, or from the axis of rotation to point P, and I'm going to take also a reference. So this is a fixed reference, and calculate or find the angle from that reference to the line connecting point B to the center of rotation. This is what I call theta, the angle. So it is theta. Note that I need to define a positive direction. Need a positive direction. And theta is, in our definition, is scalar. And always remember, work with unit. It is fine for theta itself to use angle or degrees, but unit, whenever you see it, build the habit of converting it to radians. It will simplify your life significantly along the way. So in this definition, I have defined that direction to be positive, and in this case, the angle of the body is this much. So that is angular position, or simply angle. Next thing we need to define is the concept of change of this quantity, and that is angular displacement. So if point P at a later time, let me do this, goes there, your body has gone to some angle theta prime, and you can define angular displacement delta theta to be theta prime minus theta. So that is angular displacement. Also, the way we have defined it is a scalar, and so on. Now things become quite complex or interesting with rotation. Both angle and angular displacement are scalars. They are a scalar because you cannot define them as vectors. The reason is not obvious in 2D, but in 3D rotations, you cannot add two finite displacements to get the resulting third one if those rotations, those angular displacements, are not along the same axis. In other words, delta theta 1 plus delta theta 2, let me write it down. Let me write it here. In general, delta theta 1 plus delta theta 2 is not the same as delta theta 2 plus delta theta 1. And to test it, pick up a textbook or your phone or whatever and do 2 finite rotations. First, flip your phone along its long axis, like 90 degrees, and then flip it along one of its other axes, another 90 degrees. Note the orientation and do it now. Flip the order. First, rotate about the shorter axis, then about the long axis. You will notice that you will not end up with the same orientation. So, finite angular displacements, order matters. So, you cannot define vectors because vectors v1 plus v2 should equal v2 plus v1. So, this doesn't work. However, let's go next. Let's call it infinitesimal angular displacement. If the time is very short and you only displace a tiny amount d theta, so instead of going back there, you come here, and this much that you have turned, call it d theta. If the time or the size of this displacement becomes tiny, then d theta actually becomes a vector. It is a vector, and you can again test it with your phone. Instead of turning your phone 90 degrees, try to turn it like 1 degree or a very small amount. First about one axis, then about another axis. And if the amount of displacement is very small, you notice that order doesn't matter. So in that case, you can define d theta as a vector. Now it begs the question. Magnitude and direction. What is this magnitude? Magnitude is the amount of angle, so d theta. And its direction is going to be perpendicular, or no, let's call it this way. Let's call it along axis of rotation following right hand rule. So if I curl my fingers in the direction of turning, my thumb will point to the direction of d theta, and this would be the vector d theta. Its length is in radians, however much you have turned, and direction along the axis of rotation consistent with right hand rule. So that's interesting. Now that we have d theta fully defined, we can define angular velocity. We use the term omega. Omega is a vector. It is however much you have turned divided by however much time has passed. And this is also a vector. Its magnitude is, well, how much you have turned divided by how much time has passed. And its direction, again, identical to the direction of d theta, is going to be along the axis of rotation, consistent with right-hand rule. And finally, you can define angular acceleration. Oh, by the way, this unit radians per second. Never use RPM or degrees per second or any other unit when doing calculations. It has to be radians. And angular acceleration, we use usually the term alpha. It is a vector. It is time derivative of angular velocity. Or, yeah, that's good. It is also a vector in the same way we define all other ones, along the axis, consistent with right-hand rule. If your omega is increasing, for instance, in this case, from left to right, or that direction I have drawn, your alpha will be upward. Or if your omega is decreasing, your alpha would be downward. And its unit is radian per second squared. And now you have it. You have angular definitions of position, velocity, and acceleration. You see here, there is a little bit of weirdness going on. At the position level, you cannot have vectors, but at the velocity and acceleration, you have vectors. So these are just definitions. I'm out of space, so let me pause the video here. In another video, make some comments and remarks, and we should wrap up this section. So I'll see you in the next video.